Hello, my name is David Thibodeau, and today I'm going to talk about troubleshooting with Sigma DSPs, and particularly the ADAU 1452. Um, and we're going to also talk about sample rates because that kind of falls into the troubleshooting a little bit. And yeah, and let's get started. I'm using of course, the USB-I programmer, the I2C SPI interface, and that's plugged into the 1452 Rev B eval board. And we're ready to go here as soon as I can make these wires cooperate. All right, so um, yeah, let's go right to it here. And yeah, I can shut that off for the moment. Um, yes, let's start a project. And let's see, go over here to the new projects and 1452. I'll drag one of those in. Right. Come on. Don't slow down on me now, Mr. Computer. And then I'll drag in a USB-I and hook that up. Set up the SPI. That's fine. That's what this eval board is for. And what I find in supporting customers between online and Engineer Zone and through emails is they'll set up a simple project, which is a great way to start, like really simple pass through, and then nothing will work. And often they're using a system controller of some sort, and they're trying to program the DSP directly. And so there's a lot of moving parts here, a lot of places things can go bad. So they just start with a simple project. So let's do that, and I'll show you what I see here. What I've seen is that you take an input. It's a good place to start, and take an output. And I've literally seen it sometimes with just one output. Uh, but we're gonna add a second output. And I've seen where there's a volume control in the middle, but I've seen it as simple as this. Just in to out. They compile, they work, they hit play, and they hear nothing. So, they'll go link compile download, and of course I'm going to be able to hear it here because I know everything's hooked up right. Yep, I hear it. But we'll pretend we don't hear it. So um, there's a bunch of places things can go wrong. So you kind of have to ask yourself, for starters, the very basic stuff. Uh, do I have it plugged in? Is there power? Am I communicating? Because there's audio into the DSP and audio out of the DSP that could be going wrong. There are many other settings that could be going wrong. There could be clocks missing. Um, and But the very basic is, are we communicating with the DSP? And so let me turn on that other camera and I'll show you a perfect example here. I'm going to disconnect my communications. So I'm obviously not communicating with the part. And I'm going to go link compile down. Oh, actually, I'm going to hit reset first because the program was still running in there and we would have heard audio. I'm going to go link compile download. So everything compiles because it's SPI, it's not I2C. It has no idea there's no eval board listening. It's talking, nobody's listening. And so now I hit sound and I hear nothing. So what's the problem? Am I communicating? So this is why I usually have on every project, you take a DC source, put a DC cell up there in the corner of your project. It doesn't take a whole bunch of MIPS. You can get rid of it later once everything's working, of course. And then grab a read back. Oh, that's not it. DSP read back. Put that up there. Connect these two. Hit link compile download. And if everything is good, this DC cell is now residing in a DSP. And with the read back, we're going to try to read it. And what are we going to get? Oh, we get minus 0.00000006. That's kind of an odd number. What that really is um, a very small negative number in two's complement. Let's look at the hex and read it as hex. And now it becomes much clearer. We're getting all ones, F, 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 all the way across, which means the serial data line is just sitting high. And it's reading, 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 and it's just sitting high the whole time. So we're not communicating with the part. And so now you start asking yourself, is power, is the power jack plugged in? Am I getting power? Lights, and you can obviously measure it. But one of the things is, is this hooked up, the USB-I hooked up um, to the USB port, and is that connected? And obviously in this case it wasn't connected. Now, I don't criticize anybody for making these what seems to be stupid mistakes, because uh, honesty here, been there, done that. You name it, I've done it. No power, USB-I connected to the wrong eval board. Been there, done that. Um, so it happens. I understand it very well. So we've reconnected now. Go link, compile, download, and now let's read, and voila, we're getting communications. Then you can go further. And of course, now I know this is going to work, but we can say, well, what if it still doesn't work? Well, now we're looking at the serial data, the audio data path. We've confirmed that the communication's good with the DSP, at least seems to be good. Um, Likewise, by the way, if you have a controller, you can always just send and quickly read back a memory location. Set a register, read it back, see if you can read and write from the part. Start simple. Um, and don't forget to set it into SPY mode. You need 3 writes to set it into SPY mode. So anyhow, so now we're looking at the audio path. So we have the serial port coming in. Well, there's a codec involved, though. Usually there's some sort of codec involved. We get the serial port data coming in, going into the core, and then from the core out to the serial ports and out of the chip. So here in the core, we're kind of in the middle. So let's make use of this. We can take a level meter, is the nice easy way, one way to do it, a single band level meter, and just hook that up. And you don't have to do both channels necessarily. You're just, especially if nothing's working, you just do 1 meter. Link, compile, download, turn the meter on, see what you got. Okay, I got some noise floor, but that's not necessarily bad. And voila, I can see music. Um, and this is just because I got 2 different computers and there's a ground loop. I should try to solve that. But anyways, there's see if you got audio coming in. And if you have audio coming in and you're still not hearing it, then okay, let's focus on the output. You can keep using your audio source, but an easy way to do it is just to grab another source. Grab an oscillator. And remember that these oscillators are at a very high level. They're at 0 dBFS. So I'm going to put a volume. Well, no, actually, I'm just going to be low MIPS here and say minus 30. I'm just going to lower this by 30 dB. Turn it on, put in a T connection. And I mean, I'm saying I could, actually I can be as simple as this. Never mind the T, just hook it up to 1 channel directly. And by the way, I'll show you how this works. All inputs need to be connected. Otherwise the compiler will give you an error. It doesn't know where to tell it to get data. But the outputs don't have to be connected. So this will compile just fine. And we hear tone. So I like to be safe and put a volume control and a mute. But these are things you can, and I can shut this off now. These are things you can do for just a really basic troubleshooting. Split the problem in half and see which half is the issue, and then start looking into more details. Not once you get more information and you have you can focus more in on where the source of the problem might be. Anyhow, so let's go over and well, let me start talking about sample rates actually. And since we got an oscillator here, it's actually kind of handy. I am going to put in a T connection now because I want to, I'm going to be using this probably in a project in a minute anyways, another project. And yeah, that's good enough. Okay. Link compile download, and we got tone, 500 hertz. And you notice 500 hertz, right? Okay, sounds like 500 hertz. A little bit higher than an A. I don't have perfect pitch, so don't worry about that. um, so, sample rates. There's 3 places that that things have to be right for the sample rate to be correct through the whole system. So up at the top of SigmaStudio here, there's a sample rate setting. There's a pull down box. Boy, it pulled down before I can went on off. Okay, you have sample rate setting. Once you set it, it says, do you want to default rate for new cells will be 48K, and then do you want all of them to be set to 48K? You can do this manually a few other places. All the input chains is where you set this. So you see, if you right click, you see set sampling rate, and here I can set sampling rate, or like the oscillator is the beginning of a source, it also can say set sampling rate. So that's sort of how that works. And there's another cell up here that says propagate sampling rate. That means propagated throughout the schematic and make all the cells the correct rate. Because you could have drug something in earlier and it was set at a different sample rate. So what the purpose of this sample rate is to tell the compiler what rate to compile the code to. Anything that needs timing. I mean, earlier I had shown that the meter, in an earlier video, I showed that the meter takes, does a read every 10 milliseconds, and so it sets a variable to 480, because that's 480, 10 milliseconds is 480 samples at 48K. But if we're at 4841, it would need to be a different number. Likewise, oscillators too, and filter coefficients for the cutoff frequencies and such, or the center frequencies. That all depends on the sample rate, and so the compiler needs to know what the sample rate is to compile the code properly. So it compiles the code, it downloads it to the DSP. It has no idea what the DSP is really set for. SigmaStudio does not have the intelligence here to go into the hardware config and the register settings and understand what to set up here. So to set up the sample rate correctly, then the third piece of this is what clocks are you sending, say. So you could have 48K set up in the compiler. You can have 48K set up in the register settings, and then send it an oscillator that's half the rate. And guess what? You'll have a sample rate that's half the rate. So that has to be correct as well. So the first clock control page obviously is pretty important. This DSP has a main PLL that then will drive the whole system, and that you have to set up properly. You really need it. You cannot run this DSP faster without it. So it has an input divider. Well, the source. Oh, I should mention this source. This is the worst name register, PLL clock source. It is not the PLL clock source. The PLL's clock is sourced from the pin, the master clock pin. This is the system clock source. Do we take the output of the PLL, or do we take the master clock directly from the master clock pin? That's what this register is for. So you always want to have this set to PLL clock, because it's expecting 294 megahertz signal, and if you send it a 12 megahertz signal, guess what? The DSP is running extremely slow. So that should always be set to PLL clock. And they get 96 and 4. Now this is set up for a 12.288 megahertz oscillator. The data sheet goes into all the various frequencies and things you can use and settings, etc. I won't bore you with all that here. But that sets up the basic PLL output frequency to be 24.912 megahertz, a known rate. The master clock out is an oscillator output pin that often goes to drive the codec, and in this case it does. So this has to be set for 256 FS or 12.288 megahertz on a nominal system. One little thing that you need to know is this: you can't change this with the clock out enabled. You have to disable it, change it, and then re-enable it. So it's kind of a funky little thing that it doesn't take the setting until you disable it and then re-enable it. So if you start flipping that and you're wondering why it's not changing, if you're looking at it on a scope, that's why. And then we have the other clock generator 1, clock generator 2, clock generator 3, which we'll talk about more in a minute. So this sets up the PLL. And then we have, let me go to the serial port first. Then we have the serial ports. No. Take that back. Let's look at the data sheet. Let me get this out of the way. Okay. Here's the PLL I was talking about. Divider by 4 times 96, feedback divider, 12.288 megahertz on the master clock pin. And then after this, it goes out as the system clock at 24.912 megahertz. Then it also goes, as part of the system, to 3 different clock generators. They divide the system clock by 1024, and then there's an N and M setting for all these. And you can then, this clock generator puts out 5 different frequencies. It's 5 different, there's dividers in there. So 5 different divided outputs of this clock generator. And so if you set this up for an N of 1 and an M of 6, you're going to end up with this middle rate of 48 kilohertz. And then you can go up times 4 and down divided by 4. So that works out well. And then often the defaults is that the clock generator 2 is set up with 1 and 9. And so there you end up with 32 kilohertz, 64, 128. And then clock generator 3, you can set up with 49 and 320 and end up with 44.1. So you have a lot of flexibility for clocking on this part. But clock generator 1, 2, and 3, you got to be aware of what you set them to and for the rates to be correct. So with that in mind, we go to the serial port tab. And here are the 4 serial data input ports and the 4 output ports. And you'll note that there's a clock generator setting. So here's where you select generator 1, 2, or 3. And almost always they're going to be a clock generator 1. Then off of that clock generator, remember each of them have 5 frequencies. Here's the 5 frequencies that you can choose, those dividers. And the middle one was the FS, or 48K, then divide by 2 or 4, or multiply by 2 or 4. So here's where you set up the serial ports rates. And this is assuming it's a master. In this case, it's a master. If we set this to slave, then it's just going to be whatever frequency is coming in. And then that's another variable. If you're not running at the proper rate, then what do you got coming in if you're running the serial port as a slave? So anyhow, I'm not going to talk too much more about the serial port here. We're just talking about clocking and sample rates. So this is all pretty important. And then, okay, so that's the serial port sample rate for the data coming in and data going out. Now, the core has its rate of how often it's going to run the program. Because remember, these things start at the beginning of a sample period, run the program, and then finish and store their data away, and then wait for the next sample period. And so it needs to know, when do I start? When do I start? It's just going to wait. So that is the start pulse of the core. Obviously you have the cores running, and these are the things I can discuss in another video. But the start pulse is very important. In this case, we're using the base FS, which is clock generator 1, the center. The FS is for clock generator 1. It doesn't say it there, but that's what it is. And then there's settings. Oh, yeah, I say I have to look at a database. Some of these are clock generator 2, and I think one of these is clock generator 3. So you have a few choices here. And then you have the serial input ports or serial output ports. If they're running as a slave, you can slave to that rate coming in. Then everything can be running at the same rate. And then the SPDIF receiver rate. So you have several different choices. In this case, we're running as a master, so we'll keep it at the internal clocks. So you have a choice of various internal clocks and a bunch of different output external clocks coming in. So really, really flexible. So to set the sample rates, we got to have we got to have the software set up right. We got to have the hardware set up right, and then we have to make sure we have the right crystal or oscillator sending to the DSP. I mean, I could show this. You can see I can go. I can set this to 96. Say yes. Link compile download, and then listen, and it's no longer at 500 hertz. It's now 250. Because it's running, the DSP is running at 48, and I told it to compile for 96 kilohertz. So it's running at half, the oscillator is running half the rate. So that's pretty common complaint. Say, my oscillators are running at half the rate. And as a side note, I don't know how many videos I'm going to do for the Sigma 200 for the 1761, but the 1761 has a kind of an odd way. What happens when it runs out of MIPS is it just keeps going and ignores an interrupt, and so it ends up processing every other sample. So in the end, it acts like it's running at half the sample rate. But this core doesn't do that. When the interrupt comes in, it starts over again at the beginning of the program. So what that means is it doesn't reach some code, and so all of a sudden an output's not working, or something else is not working, a meter's not working. It's because it's never being reached. But that's again another discussion. Where do I want to get to here? What am I doing? How am I doing at time? Not great. Okay. Then what we want to do is use a lot of DC cells. Things like that can be very helpful. I'm going to get rid of this oscillator. Tell you what, I'm going to jump. I'm just going to do like they do in the cooking shows, and and drop in and pull out from under the shelf. We're going to pull out something that's already cooked. So let's pull out the pre-baked ham here, and come on, you can do it. It's a little slow running this software. Okay, this is what I was going to build. What we pulled out is a volume control from the volume controls. I'll just show where I got these from, and adjustable gain, and then hardware slew. Oh, actually, is this in the software slew? No. Oh yeah, right there. External volume. Gosh, sorry. So I pulled in the hardware slew external volume, and then so you have an external control, and we're going to take the audio, the control of the volume from an aux ADC, and we're going to have a pin for a GPIO for muting. It's a good time, I think, to turn on this a little bit so you can see what I'm doing. Let's link compile download, and let's hear this work. There's my volume control. And then GPIO 6. Oh, hold on, I gotta shift play. GPIO 6 will do the mute. Um, or will it? Oh, I get to do some troubleshooting. Is that GPIO 6? Yeah, it should be. Ah, this was working. So let's do a continuous read and see if I'm getting anything. I'm not. Well, that's interesting. Oops. Okay. Yeah. Well, let me get back to that in a minute here. Um, I wanted to talk first about the aux ADCs. This is the aux ADC in the 1452 is different than the ones in the 1701. 1701 comes already shifted left 8 bits. This is a 10-bit aux ADC, but it's right justified in the data. So it's a small number. So we have to use the shift command. This core also has an arithmetic shift built in. It's easy to do. It doesn't take a lot of MIPS. So we're shifting over 14 bits to move this up so that the data we get goes between 0 and 1. And oops, I have continuous read here on continuous read, and you can see it goes down to 0. Then I turn it all the way up. It goes to 998. It never quite reaches 1, but that's okay. And so that's our volume control there. And that's coming into this ABCD block, which is in the logic section. So if you go to basic DSP logic, you're going to see ABCD out condition. This block's very handy, and I set it for greater than. So if A is greater than B, then you'll take C for the output. If A is less than, if it's not true, then we're going to take D. And D I put in a DC cell of 0, so it'll mute. It'll put out a 0. Now this volume control takes a control from 0 to 1. It's a gain factor. So it's a 0 would be mute, a 1 would be as loud as it could be. So now, why is this GPIO 6 not working? Well, let me go to the hardware configuration. Oh, I hate when that thing, I'm just going to move this a little bit, then it pops up. Okay, let me make sure the multi-purpose pins are set up correctly. This project did work and I loaded it in last time. GPIO 6, multi-purpose function, input from pin. Well, did I damage my board? Oh, user error. It helps to read. Um, it's funny. See, this goes to show you troubleshooting. I just checked a few things. If we look on the video here, I was flipping this switch. That's GPIO 8. GPIO 6 is way up here. So now it should work. We can watch it and listen. Ah, there we go. You see it changed to 1. I'll keep it muted for a second. The GPIO on this DSP is also different. It sends out LSB 0 or 1 on the LSB. It doesn't left justify it to a 1.0 or 1.23, 1.24 number. So I shifted this up 24 bits so I can get a number that's larger than A ever could be. Then that becomes true. And that's why, because this will never reach 1. And so if I send a 1, then it's going to be greater than A at any time. And it'll switch from take the output, instead of taking C and sending C to the output, it'll send D to the output. And that goes to the volume control. And then the volume control will slew down nicely and slew back up. And it'll be nice and smooth. Ta-da. So anyways, that's enough, I think, for this video. I'm trying to keep these to 30 minutes, and I'm right at 30 minutes. Oh, I guess I can mention one other little thing. If something's not working, you can always take a DC cell. Like if none of this was working properly, just drive this with a DC cell. Check that the volume control is working. You know, there's a lot of things you can really do. You can put counters, you can put other logic in, you can set up timers or whatnot. There's depends on what the problem is, of course, but there's a lot in Sigma Studio you can do to make sure and look and make sure your program's doing what you expect it to do, and then and test it one piece at a time. Um, so, anyways, I've hit my goal for the day here. Thank you for listening, and have a great day.